All right, so the title of this is Modeling Like It Matters. It's very, very difficult to give a talk like this in 35 minutes. So I decided instead that, it's so much better when it works. I decided instead that I would give 3. So I'm going to give one talk on science, one on psychology, and one on the game, which I'm sure is why you're here. The first one, science. So we've all seen this before, and my goal today is to tell you nothing that you haven't heard before, but try to remind you of some things that you'll conveniently allow yourself to forget, and hopefully help to draw some conclusions from that. And another convenient thing is that my conclusions are essentially the same as Reid's, and that is that your job at this point in your career, and really throughout your career, is to try to use data and models to try to tune and refine and train your intuition. And the importance of scientific intuition can't be overstated. And I think if you look at the older people in the room, if you have respect for them, if you respect their science, it's probably because they have this intuition, this ability to see the questions to ask and the processes to follow up. So I'm going to talk a little bit about training intuition and why that's necessary. So the scientific method. You can jump into the circle anywhere you like. Let's say that we start with some observation, we build a theory, we build some hypothesis that leads to a model that will generate predictions, and we take those predictions and we test them against data. So this, of course, is the place where the magic happens. This, when we collect the data, it is the only thing that can convince us to let go of our cherished theories. It's only when our theories don't match the data that we are willing to do what science claims to do, which is to really be open to changing your mind. It is the one thing that makes science different. Actually, the one thing that makes science different is that it's our job to find the data that is most capable of testing our cherished theories. If we do that, then we have some faith that science will progress. And through this, we'll continue in this circle, but something will be moving towards something, maybe towards the truth, maybe towards greater knowledge. At any rate, we will make scientific progress. Now, of course, we all know that science never progresses this way. It looks something like this. We have many times when we're not really making any progress. We might even be moving backwards. Other times where it seems like things are just going really crazy. We're making great progress really quickly. And of course, if you've done work on anything interesting, you're not the only person working on it, right? So that means that there are many groups, many people working on a concept, and they're following their own paths. And these paths, as these paths diverge, that's the other place that the magic happens. It's really only when we have this tension between different ideas about how to explain something that anything can change our mind. And really, again, I'd like to stress that the whole point of science is continually changing your mind. That's where it's interesting. All right, if we look at one of these paths, we see that it's moving out through time, and of course other paths are moving at the same time, and it might make some kind of crazy conceptual map that looks like this. I've labeled the y-axis model space, for lack of any better term. And we can have differences in the history and development of theories and concepts, or on the very fine scale, it might be things like, what is the hydraulic conductivity distribution, or what is the boundary condition? At any rate, if we look at any physical system at any time, we can come up with a very large number of models that can describe it, underlain by different theories, different parameter values, all of this, right? So we have this very large model space. And if we look at any one time, we may not care very much about how we got there, but it is very important that we have this broad and diverse model space. I'd like to represent this model space in a slightly different way. We often think of showing parameter space, one dimension for each parameter. Beyond 3, it gets very difficult. So we could have anything. We could have the shape, the size, the rotation, the smell, whatever it is, some way of representing that we have many, many different models. And these might all be of a same conceptual model, but differing in other elements that are along the left side here. And of course, different conceptual models also give rise to this vast forest of models, if you want to think of it that way. Many, many ways that we could describe any given system. Well, from this, of course, we have to figure out which of these models actually do represent the system. So we can take some small number of these models to start with, and I want to say, well, how can I determine which of these models is most reliable or most accurate? And that, of course, requires that we compare it to data. So now I want you to switch from model space to data space, and think along the x-axis as every possible thing that you could measure that your model could predict. Because if your model can't predict it, you can't really use it for data, right? You can't use it to test your model. So in this sense, we have this whole range of things that we might predict. We have this one thing that we've chosen to go out into a field, and we put a well in this location because it's close to the road, and then we got these data. We collect the data, and now at this point we can start testing concepts, right? Which of these underlying concepts or underlying parameter sets is more realistic? And if we do that, we end up in this kind of likelihood space. There are many, many likelihood models. It's not that productive to talk about the different flavors of them right now, but they do have two things in common. The first is the likelihood of a model is inversely proportional to how poorly it does in replicating the data. Or a nicer way to say that, a model is more likely if it does a better job of predicting your observations. The other thing, and this is very important, is that these likelihoods somehow sum to one. It's a complete problem. Even though we know we don't have every model represented, we are dealing with this as if our data is comparing among a complete set of models, of representations. And what that means is that the world is a zero-sum game. So if I go out to collect data, what I'm trying to do is make some models more likely at the cost of other models. So it's this trade-off. The reason that I collect data within this modeling context is to shift the likelihoods from one set of models to another. Now, of course, I could do the same thing with all of our models. We just end up with this much more smooth and complete distribution of model likelihoods on the right. As I said earlier, you have many, many different things that you could measure. I might have chosen to measure something on data space that's here instead. And if I ran my models, I might see something like this. Now, let me ask you, can you tell me why it's better to collect the data on the left than the data on the right? Hopefully it's fairly obvious. If I collect the data on the right and I compare it to my models, all of my models are likely to either be right or wrong, right? The wrong might be interesting, but if my models are complete, basically it's going to tell me nothing. If all of my models predict the same thing, there's very little value in collecting that piece of data. So before we ever collect the data, we can say something about which data is more likely to be useful. Becomes more difficult if I have a data set like this. So I've proposed two different observations. These are my model predictions. Which one is better? Well, now it depends, right? It depends on what I want to distinguish or discriminate. If I want to discriminate them by shape, because that says something about an interesting process, then I would choose the ones on the left. If I wanted to discriminate them by color, because that says something about some important prediction that they make in common, then I would choose the ones by color on the right. Does that make sense? So essentially we're building this case that the reason that we collect data is to try to discriminate models into different groups. And the first thing that we have to do is decide what those groups are. And this feeds very much into this group that's looking about the difference between calibration and prediction. Calibration on the left, prediction on the right. Okay, now if I decided that I want to distinguish these groups by shape, then it becomes fairly simple to come up with a measure of how discriminatory each data point might be. And essentially, we're just looking at within group, what is the spread of predictions within group compared to the spread of predictions among groups. So the more clustered our measurements are and the less overlapping, the better. They're more discriminatory. All right. Okay. Now, if we're doing science, we get to choose, or in fact, we have to choose. What is it that we want to test? Parameter values, model concepts, whatever it might be. If we're actually using these models to help somebody make a decision, they have to choose. And this is a very important distinction and one of the key differences between this inversion and prediction. If we're doing prediction to help people to make decisions, we have to engage them at the onset, because that should not only define which models we're building, it should ultimately define what data we're collecting. And we almost never do that, right? So that's something we all know, but we conveniently overlook. So what is this model importance? Well, this is a difficult step, and I'm going to present it as if it isn't. We have this forecastable quantity, anything that the model can predict. We have three different stakeholders, and some stakeholders may have interest in some predictions. And in fact, if we can translate what those predictions are to the questions that they're trying to ask, we can probably help them to determine these thresholds. Anything that predicts loss of base flow more than this value is really of concern to me. Any other model really isn't. Anything that cause drawdown at my well of more than 3 meters is really of concern to me. Anything isn't. So it allows us then, if we overlay the model predictions on these stakeholder predictions of interest, then we can say which models are models of concern. These are models that exceed the limit that the stakeholder has presented, and other models. So now we have divided our set of models into two sets, and now we're ready to go and look for data that can actually support the decision. This is in direct contrast to what we usually do, which is to do everything we can with our models, come up with this beautiful package of a model and hand it to a stakeholder who then says, how am I supposed to use that? Right? So we have to engage them early. Okay, so that might be what stakeholder 1 decides, and of course stakeholder 2 would have a different decision. They may have different data, but in many cases they may actually identify data that are common among different stakeholders, even though their questions are different. In this case, it's an easy way for people to collaborate with one another without ever having to have any agreement about their objectives. Now, how do we make use of this? We have these models that are listed out by likelihood, and we can call something like a decision confidence index or something like that. If I had to make a decision, and the colored models are models that worry me, and the gray ones are ones that don't, I would be very unhappy with this outcome, because there are very high likelihood models that are good and are bad. So now you've thrown it back on me and essentially said, I can't tell you with the science which decision you should make. If, on the other hand, I have something like this, I would be very confident. I'd be unhappy, because you're saying all of these different storylines that are different in many ways, they all come up with the same conclusion. You have a problem. And so I'm confident but unhappy, and here I'm confident and happy. So this is really what we can try to do. We can try to look for data that segregate models to support decisions. And one way to think about, I'll talk about that next. So, summary of talk 1. Multiple plausible models can and should be built for any system. Model likelihoods are, to some degree, based on fit to the data. That's all we have to represent reality. It should be the best, most discriminatory data. The expected value of these data can be predicted often before we ever collect them, which is often the most expensive part of our investigations. Stakeholders have to be involved with deciding what's important. It's their decision to make. And then lastly, what we're really looking to do is to segregate models. And the more diverse those models are, that we can still segregate into different groups, the better. All right, that's the end of talk 1. I can take a couple of questions if anybody has. Yeah?
Can you go on the previous slide?
I think I can. Oh, like before the... Can I? Yes.
Why would you be happy with less likely models?
You would be happy in this case because what it's saying is all of these models that I'm predicting are really problematic don't really fit the data. So come up with a bad case for me, a description of what might go wrong. I'm going to build a model like that, and it's going to end up in low likelihood. So I've collected models that say all of the bad stories are false, and it's the good stories, from your perspective, that are true. Yeah?
Is it a marginal likelihood?
In this case, it would be a marginal likelihood, I would think. Yeah. All right. Yes, Jay?
Yeah. What about the prior? Because the likelihood could say that the model fit is great, but you can create a model that's totally unrealistic and therefore has a low prior uncertainty or prior rate.
Yes, I'm going to quote a previous speaker. I did not pay Jeff to ask that question. It leads perfectly into the second talk, but if I don't cover it in the second talk, please ask, okay? All right, can I go ahead? Good, second talk. Okay. Wake up. Talk number 2, psychology. All right, so this is all premised, at least in the practical sense, it's all premised on being able to ask stakeholders to make some connection between what they think or what they're worried about and what we can propose as a plausible model. And this is where I think part of the answer to Jeff's question comes in. Our responsibility is to try to translate their concerns into a plausible model that can be tested. Now, part of the problem with this is that stakeholders are unfortunately human, and that means that they are biased. It's not our job to tell them how they should make their decision or what the basis for their decision should be. But we also can't expect that just by presenting the science, we're going to change their mind. They bring lots of different biases to the table, and they will make decisions based on these bias bases, whether you like it or not. And so in many ways, what's more important, and this Daniel Kahneman's Thinking Fast and Slow is a great review of many of these biases. But what's important for us is to try to think about what is the role that science can play in a naturally biased decision-making process. Okay, now unfortunately there's another part of that, and that is that we are also human. We are also biased. Once we build a model and we spend 1,000 hours building it, and especially if we're the only people in the world that can run that model, we are pretty sure that that's the model that you should use. We're pretty resistant to changing our mind about our model. So many other biases come in, but essentially what we end up with is a bias on both sides, and we're trying to answer a question that's often framed in an assumption of rational decision making. So what do we do? Well, I think what we should do is just embrace it. We're going to be biased, so let's just be really good at being biased. And how do we do that, right? Well, I think first of all, we allow for the stakeholders to be biased, and we say, what's on your mind? What do you picture? If they're going to put a well over there, what do you imagine is going to happen that's making you reluctant to have them put that well in? And they say, my well is going to go dry. Then you, as a biased modeler, come up with plausible models that actually end up with their well going dry. We are the best capable of doing that. We do that anyway, right? We're just not allowed to say that we do it. And sometimes we're arrested for doing it. But we can do this. We can build models that essentially move towards a certain conclusion or another. All right, now that sounds terrible. It sounds like the worst recommendation you've had all week. But the key to this, and I won't comment. So the key to this is that my contention, and I'm very nervous to say this with Jeff in the room in particular, but my contention is that an ensemble of biased models is no longer biased. If we get multiple stakeholder groups and we get multiple viewpoints, really what we're trying to do is make sure that we are exploring the edges of model space. What are the most different models that still satisfy our data? In contrast, often what we do when we're trying to do inversion is we spend a lot of time right around the maximum likelihood. We have a really, really good idea of the models that fit the data really, really well, the data that we have, and we spend very little time exploring those other models. Even though we know we have so little data, we often might as well be throwing darts at a board, right? So the idea then is that we should encourage each other to try to come up with very different concepts. This also, of course, applies in your science. It's very comfortable to have an idea in mind and build better and better models that represent that idea and spend exactly 0 time on testing alternative hypotheses. How else can you fit the data that you have? All right. So this is what we're looking to do. Essentially, we want to get this ensemble of models, and then how should we look at it? One way to think of it is the way that, that Lincoln's cabinet has been described. Think of every model in that ensemble as an advisor. If all of these advisors were to agree that taking an action would be good for you, it's pretty easy to make that decision. If half of your advisors say you should really take that course of action and half of them say you shouldn't, then you need more information, you need more data. When your advisors agree, it's simple. So whether they agree that it's a good decision or a bad decision, it's relatively simple. When your advisors disagree, especially those advisors that are most trusted to you, that's when you need more data. And this should really be what's driving us to say you need more scientific investigation in this case in order to untangle whether or not the predicted outcome is good for you or not. That's talk 2. Okay. Decision making is inherently biased. You will always have bias in the decision-making process, no matter how hard we try to wish it away. Model construction is inherently biased. We have a limited amount of time. We tend to become more and more expert as our models require more and more expertise to build. So we might as well embrace that. And we might as well actually embrace both of these with the goal of exploring model space. And really, a good way to say it is in exploring the important parts of model space, important for the decision-making process. Discriminatory data, we can look from our ensemble of models. We can say which data are likely to be useful for each question. And ideally, we can find data that have multiple values. I shouldn't have shown this before I asked for any questions on part 2, because I imagine that's it. All right, I'll have time at the end as well. All right, part 3. Talk 3, the game. Okay, I asked each of you, I tried to ask each of you to play this game with me. In case you didn't have a chance, I'll review it. We have a binary permeability field. The white is high K, the black is low K. No flow across the top and bottom. We have high head driving towards low head. So we have a flow system that is largely from left to right. interesting tidbit, about half of you turned it so that the flow was from top to bottom. I have no idea what that means, but I'm sure it's interesting somehow. The fields ranged anywhere from 40% high K to 70% high K. There was a total of 17, and each of you were given 5 and asked to order them. Now, in this case, the permeability difference was 2 orders of magnitude. And when you run the fields, let's see what that's not working. When you run the fields, you find that you end up with 1 order of magnitude in hydraulic conductivity across all of those grids. So it was actually pretty challenging. Usually would say, if you get K within 1 order of magnitude, you're fine. So in some ways, you would have been fine to give me those grids back and say they're all equivalent as far as a field measurement. Okay, so we have this range of permeabilities. Now, I just had a master's student who ran this, and he looked at 1 million grids, looking at 10,000 grids at every 2% or 1% change in permeability across all range of permeabilities. These are limited. On the top, we have the arithmetic mean average. On the bottom, we have the harmonic mean average. So a few things, at least for me, turned out to be quite interesting. First of all, the low K part of this is all pretty much the same. You get up to about 40, even 50% high K, you might as well give those grids back to me and say, you can't tell. They're effectively the same. Now, I asked you to look in this area because you're a challenging group of folks, and so I gave you the challenging part of the figure. But in this area, what was interesting to me was that when I gave it to people and I watched them do the test, they spent most of their time here. They really agonized over these low K grids. Like, is this one higher than that one? Now, in some ways that makes sense because they were probably closer to each other. But interestingly, out of the 70-some people who did it, nobody asked, how are you going to use this, right? So do you really care if they're different in the 3rd or 4th decimal place? Or is it equally important to get the 4th and 5th one right or the 1st and 2nd one right? So again, just a tidbit of what we found. The other thing that was common that people looked at, they said, well, visually I can tell, and you can see here, that the percent high K is important. The whiter it is, the faster it will flow. The next thing that people would say is, well, I want to find percolating paths. Percolation has somehow percolated our field. And we end up, if you look at percolation, it's a few interesting things. The very white area on the bottom are fields that do not percolate for any realization. The middle gray has some fields that percolate and some that don't. And the black is all percolating fields. What's interesting here? Percolation, yes, it's important, but only if you really care about low K materials, very low permeability systems. Otherwise, 90% of all of the variation happens after percolation, right? So down here, you might as well say it's harmonic, or you could even say it's constant. And up here, what happens is basically, it is simply counting up the number of unique paths that go through the system. If you count up, if there are 2, it's much less than if there's only 1 path, which is much more and much less than if there are 3. It's really that simple in the end. Now, it's not really because it's hard to see those paths. But if I were to ask you to do this again, I would expect that your scores on these would improve. So that leads us to this. How are your scores on these? So this is our overall percentage. So as a group, we could explain 79% of the variation in hydraulic conductivity. Now, if I was talking to a room of biologists, are there any biologists still here? That would be fantastic. That would be a science paper if you can get 0.79. For us, I think we would expect that we might be able to do a little bit better than 0.79, but still no. We see, interestingly, that the mistakes were made at the low end and at the high end. And again, very often people would put down the top 3 and say, well, I know those. Let me spend my time over here on these other ones. And by the end, I could watch and say, well, you think you know those, but you actually are getting these that are most different from each other. You're getting those wrong as well in about equal number. That's interesting, but it's not really why you came to the talk. Why you came to the talk is to see really how people did. Out of the 70-some people, 9 people got it entirely correct. Faculty, 1. 1 out of 25. What it means, so this is basically the number of mistakes. So to get 0, you had to have all of them correct. 2 would be basically you swapped a first and second, right? Or a second and third. 4 would be you swapped a first and third, or a third and first, something like that. So these are the numbers for faculty. It is not statistically different than if they had just handed the cards back to me and said, I refuse to play. But nonetheless. Their overall score is 3.44. Now, the other thing that I heard the other day was that, I might get the number wrong, but something like 80% of French men who are polled think they're better than average lovers. So I'm not going to tell you who the faculty member was who got it right. So I'll let you all off the hook that way. Postdocs. Yes, please.
Yeah, just another common question could be, what if these were student applications?
What if they were anything else that we have to infer? Yeah, absolutely. Postdocs, 20% right. Average score 3, a little bit better. Remember, a lower score is better. Students, I would have loved it if you guys did the best. And you came very close. 6 of the 9 that got it correct were students, but your overall score was the best. So, what does this tell us? I think that it tells us something actually that's fairly important, even though it's a small sample and it's a poor test. But I think what it's telling us is sometimes you're better off not overthinking a problem. Sometimes the more you know, the less you're willing to just look at a problem holistically. At least that's the message that I want to get across. All right, summary of talk 3. So the idea here, and why I want you to do this, is I think that there are many things that we can do where we do games like this, or we do simulations, and we look at the simulations just like Reed was talking about, and we try to train our intuition. So how can we do better the next time that we are asked to do something like this? Now, when are you going to be asked to do this again? Probably never. But what's really important is, what Nicholas said earlier in the week, is when you go to do an inversion and you impose, say, some kind of structure on a system, that structure invariably shows up in your inversion, no matter how much fancy mathematics you do in a sense. Yeah? So if I'm saying that you should try to be proposing models that are very different from each other, until you can actually understand, say, what makes hydraulic conductivity fields different from each other, it's very difficult for you to think creatively about models that are different. So this kind of intuition can work on both ends of a problem. The obvious conclusion. All right, summary of all 3 talks. Our job is to propose plausible different models. This is very difficult to do. It is not what we are generally trained to do. It is what we tell the public that we do. Then we should be looking for discriminatory data. Again, I'm not sure how many of you, would anybody say that they've done an exercise where they look for discriminatory data before they collect it? 1. You probably got the grid right too. Yeah. All right. And this can be guided by stakeholders' interests. And it should be, in fact, for applied problems. This is not a taint on our science. This is actually just making sure that we're answering the right questions with our imperfect models. And all of this requires some kind of trained intuition. All right. With that, I'll finish. And I think if I have time, I'll ask for any questions.
Clarifying what the right questions are, what the good questions are?
I think we can. I think in some cases we can. I think not as often as we think we do. But I want to clarify that a little bit. I think that essentially, I think what we should be saying is, what are the uncertainties, what are the predictions, what are the outcomes that are really going to drive your decision? And then we can try to translate that into something that our model might predict. Some of them we don't have anything to do with, right? But those that we can actually make predictions, and the uncertainty about that prediction will guide the decision-making process, that's where we can focus. And at that point, once we have that guidance as to what part of that model is important, or what predictive capabilities, then the science can take over. Yeah? Yeah, please.
During the game, did you clearly state or somebody asked you that the flow was obeying the Darcy's law, or we are biased by this environment?
It's a very good question. Yeah, nobody asked. Yeah, nobody asked what the gradient difference was, right? I mean, although, yeah, exactly. It's also a good question. Now, one person did ask if I used mod flow or if they allowed to have corner-to-corner flow. So some people got into very, very detailed parts of it, but not on that level. Yeah, good. Yeah.
I have a question about what you said about the modelers being biased.
Yes.
But we have to test all possible possibilities. Reality. So how do we make sure that we cover all possibilities?
We really can't. We really can't. And so I think in part that's the reason to work in contention with other modelers who will bring other concepts and other biases to help us to explore that model space, a really model important space. But I think that at a minimum what we can do is make ourselves think at the conceptual back of the envelope level first. Because those models you can run 10 or 20 of them in an afternoon. but it requires you to let go of some precepts where you say, well, I'm going to assume that, like Reed said, I assume that hydraulic conductivity averages the geometric mean over this pixel. And then you think, well, what if it doesn't, right? What if we have some kind of bias this way or bias that way for whatever reason? Would that make a difference? So starting to do that almost very crude sensitivity analysis at a structural level, I think, is one way that we can do it. Yeah. Yeah.
I'm just a bit confused because I feel like you gave two contradictory messages.
Probably.
You showed that the people who had the most expertise and in a way are the most biased were also the most wrong. But on the other hand, you were saying that making models in a biased way is something to aspire to, I guess, for better decision making. I mean, is it a wise decision to make wrong predictions?
Yeah. So it is not a wise decision to make wrong predictions, but it is a wise thing to say, if this is the outcome that you care about, let me think of all of the plausible or somewhat plausible storylines that could end up in that place. Because until I've done that, I don't have any way to test them. So in that sense, it is worth making models that are as good as they can be, but still make wrong predictions, because then you have something that you can test. As far as this importance of the training or expertise, I think that, and again, this is a very small sample, so I'm extending beyond reality. But I think that what we could bring from this is that the more we learn about something, the deeper we get into some way of looking at a system, the harder it might be to break out and think in some other way. And I don't generally think, and maybe it's just my ignorance on this, but I don't generally think that this concept that number of percolating pathways is the overall thing that's controlling permeability is something that we tend to think of in general. Yeah. Yeah.
Another thing, so I think I would like to offer a different explanation for those results.
Great. Are you in one of the winning groups or the? Yeah. Yeah.
So can you show the
I think so. Yeah.
one with the years and stuff?
You mean these grids? Oops. Oh man, now I've done it.
If you get that.
You want to see the grids with the different percentages, or?
Plots where it shows
Like this one?
Yeah. So
Okay.
we've kind of shown that intuition doesn't do everything, and that's kind of my point. But, it doesn't matter. So I would claim, intuitively, although I could be completely wrong, that these are all statistically the same.
Statistically the
So
same.
we basically all feel the same. But
Yes.
I would say also that it makes sense because you gave us the hard data.
I gave you the hard grids to do.
So
Yeah.
at this point, intuition is probably not doing so well. And in our defense, I said that most of us would not make a strong claim that we know what the outcome will be without sitting down and actually shutting up and calculating.
Fair enough. And the thing that I've found in some ways the most interesting about this, an even smaller sample size. But my student, when he took some of these grids home, he asked his mom, he asked people at the grocery store, he asked anybody, and they did just as well, right? So there's almost to the point that, and maybe it's just there's not enough information, it can't be determined, but I think that there's something in there that's telling us that we could all learn a bit better how to recognize some of these patterns. And this is just one example. Huh? It's anything where we have to propose a different model than the one we're thinking of. It's very hard to pull back. Yeah. Yeah.
I have a really stupid question, but how it's possible 5 to respond?
To get 5 wrong, I think you have you think the second one is the first one and the third one is the second one, and so it's the distance.
7.
Yeah, it's the No, there are five, but the distance. If you switched number 1 and number 5, you were penalized more than if you switched number 1 and number 2.
Okay.
Yeah. So it's essentially a proxy for your R squared. Okay. Yeah.
Can you maybe kind of weigh the likelihood of each model based on the risk of the outcome?
Okay, so can you?
You see what I mean?
Yeah, so this would be a probability weighted utility function, huh? And this I think that you can do that, but you run into problems where things are relatively low probability, especially when we have a small sample or we haven't completely looked at our model space, but have very, very high consequence, right? So like a black swan type event. And so my personal feeling is that if we tell somebody there's a 1% chance or a 2% chance of something happening, that's no different to them. Yeah? But if we tell them that there are 500 models that we tried to build, and only this one model says this thing is going to happen, and the other 499 say it's not going to happen, it might, in percentage sense, likelihood sense, it might be the same, but I think it gives a better context than just giving a weighted risk probability. But I think this is, and I think Jeff works in this area, I think this is definitely a way that we do this, is a probability weighted risk.